Imagine a liquid that dances to a magnet's tune, forming spikes and patterns as if alive. Ferrofluids look like science fiction, but they obey the laws of physics in spectacular fashion. What secrets lie beneath the glossy sheen of these magnetic liquids? Today we'll dive into the physics that makes ferrofluids defy our expectations. We'll trace their discovery, uncover the nanoscale magic inside, and explore real-world wonders. By the end, you'll see how magnetism and fluid dynamics merge into one. Prepare to see a liquid shape itself at will. Prepare to witness the interplay of forces at the smallest scales. Are you ready to unlock the mystery? Let's begin our immersive journey into the world of ferrofluids. The story of ferrofluids began in the 1960s, when NASA scientists hunted for liquid rocket fuel that could cling in zero gravity. They needed a way to move fluids without pumps in microgravity environments. By suspending magnetic nanoparticles in oil, they discovered a stable magnetic liquid. This new substance flowed like a normal fluid, but responded instantly to magnetic fields. Early experiments revealed spike formations at the fluid's surface under magnets. These spikes formed a beautiful, regular pattern known as the Rosensweig instability. That pattern hinted at a delicate balance between magnetic forces and surface tension. Researchers in the 1970s refined the formulation, improving stability with surfactants. Surfactant layers prevented particles from clumping, keeping them suspended. The result was a true ferrofluid, tiny iron-oxide particles dancing in carrier oil. Soon, engineers and artists alike marveled at the mesmerizing displays. But beyond the spectacle lay deep questions about the underlying physics. How do individual nanoparticles coordinate to produce large-scale structures? How can we control these patterns with precision? To answer these, we must zoom into the nanoscale world. At the heart of every ferrofluid are nanoparticles roughly 10 nanometers in diameter. Each particle consists of a magnetic core of magnetite or hematite. Surrounding that core is a surfactant shell, like a molecular skin. These shells prevent the particles from sticking together under magnetic attraction. In the absence of a field, Brownian motion keeps particles evenly dispersed. Introduce a magnet, and each particle's magnetic moment aligns with the field. Aligned particles develop chains, linking end to end like microscopic beads. These chains stiffen the fluid locally, altering its flow properties. On the surface, chains climb out of the liquid, forming peaks and valleys. Surface tension fights to smooth these deformations, creating a stable pattern. The height of each spike depends on field strength, particle concentration, and fluid viscosity. Too strong a field, and the spikes grow unstable and merge. Too weak a field, and the fluid's surface barely ripples. Understanding this interplay is key to applications in seals and sensors. But how exactly do these dynamic chains assemble and disassemble so quickly? The spikes you see in ferrofluids are a classic example of the Rosensweig instability. When the magnetic force perpendicular to the surface overcomes surface tension, peaks emerge. Each spike concentrates magnetic flux, reinforcing the pattern. The spacing between spikes follows a predictable wavelength dictated by fluid properties. Mathematically, we derive this from minimizing the fluid's total energy. The energy components include gravitational, surface, and magnetic contributions. At equilibrium, these energies balance at each spike. Disturb the field, and the pattern reorganizes in milliseconds. High-speed cameras capture the fluid dancing in synchronization with field changes. Under oscillating fields, ferrofluids can form dynamic waves or labyrinthine patterns. Some researchers exploit these patterns in art installations and interactive displays. In lab settings, precise control of field gradients sculpts the fluid into complex shapes. Engineers use this effect to create tunable optical devices and vibrational dampers. The same physics underlies ferrofluid actuation in small-scale robotics. But ferrofluids offer even more surprising phenomena beyond surface instabilities. Apply a rotating magnetic field, and ferrofluids can swim or spin in circles. Tiny droplets move in response to field gradients, like magnetic marionettes. Chains twist and untwist, storing and releasing elastic energy. At high frequencies, the fluid behaves more like a solid magneto-rheological fluid. At low frequencies, it flows freely, showing its liquid nature. This tunable rheology makes ferrofluids ideal for dampers in precision equipment. Under pulsed fields, the fluid can pump itself along channels without mechanical parts. Microfluidic devices exploit this for pumping fuel and other liquids in small systems. Biomedical researchers explore ferrofluid-based drug delivery, guiding nanoparticles with magnets. In hypothermia treatments, localized heating by alternating fields targets cancer cells. Meanwhile, in loudspeakers, ferrofluids cool voice coil heat and improve sound quality. Their thermal conductivity and magnetoviscous effects protect delicate electronic components. Even in spacecraft, ferrofluid seals prevent propellant leaks in vacuum. These diverse applications all hinge on understanding field-responsive dynamics. As we refine control methods, new uses continue to emerge. One of the coolest demos shows ferrofluid climbing up ink drawings on paper under a magnet. The spikes follow the lines, tracing hidden magnetic flux pathways. In art galleries, interactive ferrofluid panels let visitors shape living paintings. In optics, ferrofluid lenses change shape under fields to focus light dynamically. Industrially, ferrofluid rotary seals prevent lubricant leaks with no mechanical contact. This extends seal life in hard drives and vacuum pumps. In the automotive industry, ferrofluids dampen vibrations in engine mounts. They also cushion high-precision gyroscopes in navigation systems. Some future smartphones may use ferrofluid speakers for richer bass. Research prototypes even show ferrofluid-based micro-robots swimming in liquids. These micro-robots could one day clear arterial blockages or deliver drugs locally. In energy harvesting, ferrofluids convert mechanical vibrations into electricity. Imagine floors that generate power as people walk across ferrofluid tiles. Even fashion designers play with ferrofluid jewelry that changes shape with magnets. The wonder of ferrofluids lies in their endless versatility. If the magnetic elegance of ferrofluids amazes you, hit like and subscribe below. Share your favorite ferrofluid demo in the comments. Is it the dancing spikes or the self-pumping fluid? Every interaction helps us explore deeper physics topics and bring them to life. Don't forget to ring the bell icon so you never miss an experiment or tutorial. We'd love to know how you'd apply ferrofluids in your own projects. Will you use them in art, engineering, or medicine? Your ideas could inspire the next generation of practitioners and researchers. Join our community of curious minds where science and creativity collide. Follow us on social media for behind-the-scenes footage and extra insights. Check out our playlist on magnetic phenomena to dive deeper. If you have questions, drop them below. We read every comment. And if you want a step-by-step tutorial on making your own ferrofluid, let us know. Your support powers our mission to demystify the mind-blowing world of STEM. Together, we can spark experiments that reveal the hidden forces around us. Thanks for watching. Now let's continue our journey into magnetic liquids. Beyond demonstrations and applications, ferrofluids challenge how we visualize liquids. They blur the line between solid magnets and flowing fluids. At the intersection of material science and physics, they embody emergent behavior. Philosophers might ask, does a fluid that thinks like a magnet have a new form of intelligence? As we engineer ever smarter materials, the boundary between animate and inanimate blurs. Future research aims to program ferrofluids as soft robots that adapt their shapes on demand. Imagine building structures that reconfigure themselves using magnetic instructions. In aerospace, self-healing fuel systems using ferrofluids could enhance reliability. In medicine, injectable ferrofluids might navigate complex vascular networks with precision. At planetary scales, could ferrofluidic seals make fusion reactors more practical? The potential seems as vast as human imagination. But with great power comes ethical responsibility. We must consider environmental impacts of large-scale nanoparticle deployment. We must ensure equitable access to these emerging technologies. Yet the story of ferrofluids reminds us that nature's smallest scales hold grand possibilities. Every drop contains billions of magnetic dancers, following the subtle rules of physics. When we learn to guide those dancers, we unlock new frontiers of innovation. So the next time you see ferrofluid spikes, remember, you're witnessing physics in vibrant motion. Keep questioning, keep experimenting, and stay curious about the hidden worlds within.